Huh. All right, let's try this out. Right, should I start it with the normal YouTube intro where I go, hello, and today we're going to talk about the Euclidean algorithm. These are my answers for the greatest common divisor. I got 90 and 63. Isn't that exciting? Now, I would say the first one's kind of easy to do, right? Like we might be like, oh, look, that's 90. I see 90 in there right there. That's 990. That's divisible by 90. And then you do some legwork and you realize that 90 is the only thing you can really deal with really easily. This one's not as nice, right? 819 and 504. Those aren't great numbers to deal with. We might be able to know, maybe if you know your 9 trick, right? The sum of the digits add up to 9. So you know, oh, that's divisible by 9. This is divisible by 9. And maybe you divide 504, maybe you divide both of them by 9 and get what? 504 divided by 9 is 56. And then 819 divided by 9, and you get 91. And then from there, you're able to figure out that, hey, this is also divisible by 7. So you get 63. Maybe that's what you did. What did you guys do? Did you do anything different? Or did you just try to find divisors that work for both of them? You can still throw answers in the chat. That works too. Tim did the dividing thing. Olivia, prime factorized. Yeah, prime factorization I think is great here. Ananya did the Euclidean algorithm. Well, let's start there. Can you explain the Euclidean algorithm for me, Ananya?
I forgot why it works, but like I know how to do it. Is that?
Yeah,
okay?
That's fine. Explain what you did.
So I took the biggest number out of the two numbers and subtracted the smallest number from it.
Mm-hmm. And so that got you what? 270 and 720?
Yeah. And then I keep doing that for the biggest number and the smallest number.
So I'm going to subtract 540 because you can do it twice too. And so this gives me 180 and 270. And then I get 90 and 180. And then you realize you just get 90 and 0. So whatever number you end up with, the one that's not 0 is your GCD. Let's see if that works cleanly with the other one. Yeah, you can do it twice. Because what would happen is if you did it once, like let's say I do it once for the 270 to 720, then you go 270 and then you would go what, 540? No, not 540. What's 270? That gives us 450. My bad. And then you'd be like, oh, okay, well 450 is still the bigger number, so I'll subtract 270 again from it, and that gets me 180. Okay, so that worked really nicely with this one. Let's try it with this one. Let's subtract 504. And so that gets us 315. Right? Let's assume I can subtract. It's a struggle for real. 504. Yeah, okay. And then so now we're going to subtract 315 and get 189. And then from 315, we subtract 189 and we get 126. And then we get 126 and 63, and then 0 and 63, or 63 and 63. But either way, we end up with 63. Okay. Now, if you want the, I guess, more legitimate way, you could prime factorize or divide, right? Like you find a divisor, you're like, oh, right, like we talked about at the beginning, I know these are divisible by 9. But we're going to talk about the Euclidean algorithm today and what that means and how that can help us for problems like this, finding a greatest common divisor. And we'll get a little bit into this today. We'll get a little bit more into it tomorrow as well, though. Wasn't that the exact same problem? Okay, we did that one. So Euclidean algorithm says this. For the greatest common divisor of m and n, it is equal to the greatest common divisor of m minus n, comma n. So essentially what Ananya was talking about, you can subtract and keep simplifying, right? And then now if we know m minus n is smaller than n, then we could do m minus n, which would get us 2n minus m. And that's a whole thing. But we can just keep simplifying down this way. Okay, questions, comments, concerns so far? Cool. So here's a problem for us. Two different rectangles have the same width. All four sides of both rectangles are integer lengths. The area of the rectangles are 1,086 and 828. Find the largest possible value of common width of the rectangles. I'm gonna give you guys a couple minutes to do that. I'm gonna pause the video here. Pause the recording. Okay, so our answer is 6. Our answer is 6. So someone walk me through how'd they do it. How'd y'all get it?
I found the GCD of the two numbers.
Yeah, so how do we find, we were told the areas. How do we find the area of a rectangle?
Width times length.
Length times width, right? So we know length times width that's an 1086. Let's call that length 1. And then length 2 is the other one. And then we get width is the same. And so because the width is the same, we can essentially say that we want length 1 and length 2, or length 1 is equal to that over W, and length 2 is equal to 828 over W. And so we can just say, hey, we really are looking for the greatest common divisor of these two numbers. And again, with a number like 6, right, it's probably much easier to just say like, hey, these numbers are divisible by 3. The sum of the digits is divisible by 3. And oh, look, it's also divisible by 2 because they're both even, and kind of do it that way. But let's assume we went the long way in this case with Euclidean algorithm. So what's 1086 minus 828? What do you guys get? 258, is that right? We got 258? Yeah? No? Yeah? What do you think, gang? Can we subtract? Okay, we can subtract. So then you get 258 and 828. And you subtract and get 258 and what?
I got 268.
You got 268? I think it's 258.
I put it in my calculator unless I have the wrong numbers.
Did you get 1086 and 828?
Yeah. Oh, 1086?
Yeah, there you go. You put 96 in. All right, so, oh, my bad. So that put in 570, and then you subtract again. And that gets us to what? Oh, 312. Thank you, 312. That gets us 312, and we can do it again. And we get what? 54. Yikes. So now that we get 54, this is a big thing. 258 and 54. 54, let's just take that away a bunch of times. It is really long. I think we can shorten this up though. How many times do we take out 54? We take it 4 times. That would give us 216. So 216 gives us 38. 38 and 56 is, or 54 isn't bad. Then we get 38 and 16. And then that gets us 12. No, 22 and 16. So that gets us 6 and 16. Wait, I went wrong somewhere, didn't I? Where'd I go wrong?
2. It's a 42 instead of a 38.
Oh, it's a 42. My bad. Okay. 42 instead of a 38? Oh, like all the way back there. Yikes. That's called bad at subtracting. Okay, 42 and 54, and that gives us 42 and 12. And then so from there, we get 6 and 12, and we realize that that gets us 6 and 0, so we like 6. Yeah, going the other way and just saying, hey, let's deal with dividing by 3 and 2 and then see what we come up with is nice. Now, this is the other way we talked about. This is the extended Euclidean algorithm, and this applies to simplifying repeatedly, right? We know that n is equal to some integer, right? All of these are integers, q times n plus r. R is our little remainder. This is our remainder. Which is why when we do this repeated subtraction, we're saying that they have a common factor, right? They have some common factor, which means our remainder is 0. We're going to look at tomorrow times where they are relatively prime to each other, and that's going to lead us to having a value of 1. They'll have that remainder of 1, and we know, oh, these two things are, there's no factors in common that they share. Are we going to learn mods? Yes, we're going to talk mods too, for sure. Okay, so GCD, here's another way we can talk about it. This is just repeatedly subtracting. So let's take a second. Another thing I want to clarify, these are not any problems of my own. These are problems that I have yanked from the AOPS Intro to Number Theory. So keep that in mind. These are not problems that I've written. I'm not trying to take credit for them. We're just going to look over and discuss these problems. So do you want me to, let's put you guys in groups. Let's do that. Let me pause the recording again. Put you guys in groups and then we can talk about the answers after. Okay, so these are, if it'll let me move them. Nope, just making me make more boxes. Hold on. All right. Oh, see, making more boxes. And fourth time. There we go. Boom, 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 boom. Nice. What do we think? Which ones are we confused on? Which ones do we want explained? How do we feel about it?
How do you do 5?
Okay, so for 5, what we realize essentially is that we see ABC, ABD, ACD, and BCD. And specifically, there's 4 different equations there, but each variable only appears exactly 3 times. You also notice that P minus 3, P plus 1, and 2P plus 2, those will cancel out, right? So when we add them all up, we get 3A plus 3B plus 3C plus 3D equals 5P. So that means A plus B plus C plus D times 3 has to equal 5P. So we know 2 statements about this then, right? We know A plus B plus C plus D must be divisible by 5 because it's essentially equals to 5 times P. What do we know about P though? P is what kind of number?
A prime number.
P is a prime number. So we know that 5P has to be divisible by 3. And so what does P have to be? 3. Right? The only way for P to be prime and to be divisible by 3 is if P is 3. So there you go. Comments, questions, concerns. So we want to look for that pattern of, okay, if we realize A, B, and C, we see essentially a question like this where we get all these different equations. See if you can essentially eliminate or get multiple of the same variable. And chances are if the variable is appearing the same amount of times total, that's going to be a clue for us as well, right? So we saw 3 A's, 3 B's, 3 C's, and 3 D's. All right, let's keep this train moving. this problem is decently different than the other ones. Well, maybe not decently different. I take that back. I lied. What would have happened if they didn't appear the same amount of times? So going back to the previous question, if these didn't appear the same amount of times, I would not maybe try the adding up, or maybe there would be a different GCF that we could take out. So like if they all had different GCFs, then either at some point I might be able to solve for A, B, or C, right? And get some type of system that would help me simplify this even further, right? If we know what C is, then that makes this a little bit easier for us to deal with, because then we have stuff in terms of P, and now we can do matrices or a 3-variable equation. All right, Janet writes the number of cubes. This should say of, not if. Of 3 positive numbers on a piece of paper. Rob points out that each is a multiple of 18. The GCD of all of the perfect cubes is n. Find the smallest possible value of n. What do we think?
Wouldn't it be 18 because we're looking for the smallest value and they're all a multiple of 18?
What does the first sentence say for us though?
Jeanette writes the cubes of 3 positive numbers.
The cubes, right? So is 18 a cube? Yeah, 18 is not a cube, so that won't work. If 18 were a cube, I'm 100% with you. So if each one's a multiple of 18, how can we break that down? What does 18 break down to in prime factorized form?
2 times 3 squared.
2 times 3 squared. So each one of these has to have 2 times 3 squared. And so we also know that each number of these are cubes. So what would I need to have at least powers of 2 and powers of 3?
You can multiply that by 2 squared times 3, because you need the exponents to be 3. Or
yeah, we need the exponents to be multiples of 3, right? So this should be at least 2 cubed times 3 cubed. And so if I were to take the cube root of that, my smallest possible one would be 6. Radical pointed out 6, 12, and 18 would all be possible. And going back to what Vasu says, right, 18 would work, but it's not our smallest possible one because these all have to be cubes. And so we'd essentially have too many 2s and 3s if we were looking for the smallest number. Cool. All right, find the prime factorization of 200. Take a minute and try that out. Figure out how many factors this has, though. Ananya and Olive are both claiming 12. Why are they claiming this massive number? Where are you getting 12 from even? I see 3 and 2. How do we even get 12?
You add 1 to both of the exponents, and then you multiply them.
That gets me 4 times 3. So 12. Why?
Because when it's including 2 to 0, so that's more, 1 more.
So essentially we have to think about it like this. If we're trying to figure out how many factors it has, what would a factor of 200 look like? Something like 10, 20, 25. These are all factors that we could potentially have. Essentially what we're saying is, how many options do you have? Right? If I have 2 cubed, my powers are possibly 0, 1, 2, or 3. Meaning that I have 4 options that I could pick from this. For the 5, I could have 2, 1, or 0. So 3 options. This essentially is saying, hey, you have 4 options for your powers of 2, pick one. You have 3 options for your power of 5, pick one. And that gives us a total of 12 options. The shortcut being take your power, add 1, and multiply by the other power, add 1. Questions, comments, concerns on that? Okay, well, try this one then. Find the prime factorization of 168. Tell me how many factors it has, and then how many of them are even. Gonna give us 1 more minute. Oh, wow. This is, I'm being told this is 2 cubed times 3 times 7. Do we agree with that? 2 cubed times 3 times 7. Yeah, 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 yeah.
Yes.
Yes, cool. So how many factors would that be?
16.
16, I agree, right? Because we have 4 here. This makes 4. This would make 2. This makes 2. So how many of them are even? Or how could we find out how many of them are even?
You could subtract how many ones are not even.
Sure. How many factors would be odd?
4, 1, 3, 7, and 21.
Yeah, we could subtract 4. Those being 1, 3, 7, and 21. How do I know a factor is not even? What does that mean if something's not even?
It's odd.
Yeah, it's odd. But what does it not contain?
2.
Yeah, it has no multiples of 2. So we essentially just get rid of any multiples of 2. And so that means this becomes just 1. And so we can do 16 minus 4, which gives us 12. And we'll talk more, this is called complementary counting, right? It's easier for us to say how many are odd and subtract that away from the total than how many are even and then subtract that away. We could have done that too though. Oh wait, sorry, we did the other. Yeah, no, we did this way. We did how many are the total number and then subtract from the amount that are odd, not how many are just in general even. Because then you have to factor in a whole lot of other things. All right, questions, comments, concerns. Wait, what did I just say on the last bit? This is total minus, my bad, total minus odd. I think I just talked myself in circles there. Yeah. All right, next one. Oh yeah. Hey, I don't know, some of you might not have seen a problem like this before. So I wanted us to address this. This is just a fun little thought experiment, really. So a hallway has lockers. This is like an infinite hallway problem. This is what a lot of times they'll call it. Essentially, all are left open. Brandon goes through and closes every even locker. Olivia comes through and changes the state of an even locker of, this should not say even. This should say every locker. Changes the state of every locker whose number ends in a multiple of 3. So we start off with locker 1, 2, 3, 4, 5, 6. So originally they were all open. Brandon goes through and he closes every even locker. So now these ones are closed. Olive goes through and she closes every multiple of 3. So now this one is closed. This one is now open. Not sure why it went to highlighter there. And then Arjun comes through and changes the state of every 4th locker. So now this becomes open. And if we kept going, we would see that the next one this becomes closed and so on and so forth. Because this pattern keeps repeating even past when we run out of children. So my question to you is, which lockers are left open at the end of this? I'm going to give you 3 or 4 minutes to try to ponder this one out. How many lockers are there? An infinite amount of lockers. Every single locker ever created is lined up.
So
Ishan said all the perfect squares. Why do all the perfect square numbers, 1, 4, 9, 16, so on and so forth, why are these the only ones left open?
because they get changed in odd number of times.
So what does that mean about the factors of perfect squares?
They have an odd number of factors.
So perfect squares have an odd number of factors. And they're the only numbers that are going to have odd number of factors, right? This is just 1 to the first, really. That's the only thing you got. If you had 2 to the first, you have 2 factors, 1 and 2. 3, you got 2 factors. 4, well, that's 2 squared. And so now you're just going to have 3 factors total. 2, here you have, for this one, you have 4. 7, you still have 2. 8, you got 4. 9, 3, right? And no matter how we do it, because they are in even power, right? Perfect squares have even powers, then you're going to end up multiplying them. And when you add 1 to each of those numbers, you'll always end up with that odd number. Cool. I think you guys are good. I think we're at about time anyways. So we'll stop here.